derive velocity with respect to time, you get acceleration. So dv by dt, you substitute this equation in the above one. What we get? dv by dt is equal to minus E by m. Okay, so this equation we have substituted a value. Then integrating, you can do what we get. V is equal to minus E by m into t plus c. That is integration constant. The value of c can be evaluated by substituting the boundary condition, where we have to get c value, right? So what is c? We have to apply boundary conditions. When t is equal to 0, when time is equal to 0, velocity is equal to 0, we get c is equal to 0. From equation 3 and 4, we can write v is equal to, from these two equations, we can write v is equal to minus E by m into t, because c is 0. The current density is current flowing through unit area of cross section. Okay. How much current is flowing through the unit area of the cross section of the material? That is actually current density J. J is equal to I by A, current per unit area of the material. The current density is also given by this relation. J is equal to minus NeVd. In semiconductors, we have derived already. J is equal to minus NeVd. From equations, the above two equations, 5 and 7, what we write? J is equal to Ne square by m into t. Because what is V? Minus E by m into t, right? Minus E by m into t. So minus Ne into minus E by m into t. So that is why J became like this. Ne square E by m into t. From point form of Ohm's law, J is equal to sigma E. J is equal to sigma E. Okay, so from 8 and 9 equations, we get sigma is equal to Ne square T by m. Because J is equal to sigma E is equal to J by E. What is J? Ne square E by m into T, right? Divided by sigma is equal to J by E. This expression, 8th expression divided by E. We get this one, Ne square T by m. This equation, from this equation, we infer that the conductivity is directly proportional to time. It means that conductivity increases if we apply the electric field for a longer time. That is what it means, right? Because conductivity and T are directly proportional. So if you increase the time span, then conductivity increases. Material's conductivity increases. Negative sign in the equation 5. What is equation 5? V is equal to minus E by m into T. V is equal to minus E by m into T. Here, minus sign in the equation 5 indicates that the electrons are moving in the opposite direction to that of the applied electric field. I already told you, when electric field is applied in some direction, opposite to that direction, electrons will move. Here, negative sign indicates that because of charge repulsion. What are the main sources of electrical resistance? We see metallic crystals, electrons move freely. That we all know that. The cause for electrical resistance is the scattering of electrons, and the cause for the electron scattering is the non-periodicity of the lattice potentials. The causes for non-periodicity of the lattice potentials are why actually at different points of the lattice, different potential electron experiences when it is flowing through the positive ion core of the material. Why actually it is experiencing different potentials? Because non-periodicity of the lattice potentials are because of these things: impurities in the crystals, crystal defects, and thermal vibrations. These are the main reasons for non-periodicity of the lattice potentials. Freely moving electrons are associated with de Broglie or matter waves. Freely moving electrons are associated with de Broglie or matter waves. They are called matter waves, right? Material particle, if it is in motion, usually free electrons are associated with wave. They move in the direction of a wave. That is what actually matter wave is. In a perfect crystal, an electron moves similar to an electromagnetic wave without attenuation and without any hindrance. So the mean free path of electrons will be of several hundred angstroms. The mean free path of the mean free path of electrons will be several hundred angstroms. Okay, so it can have the electron, if it is moving in the form of wave, it will have the amplitude, it can go up to few hundred angstroms, the wave amplitude. You can understand now. So presence of what we understood, the impurities in the crystal, that is one of the reasons for resistance that is arising in the solid materials. The presence of impurities introduces electrical resistance in a metallic substance. With an increase of impurity concentration, the resistivity of the metal increases as shown. Say this is rho resistivity versus temperature in Kelvin. For pure material, pure conducting material, here resistance goes like this with increase of temperature. For impure, it will be. For more impure, resistivity values are going up and up. See, for pure material, it started with 0, and as you raise the temperature, because of other parameters are playing the role, that's why resistance is getting hiked. Otherwise, for pure material, resistance will be almost 0, because if it is not having any impurities, electrons move very freely. The presence of impurity at atomic site changes the periodicity of electrical potential. If the impurity concentration is more, then at large number of atomic sites, non-periodic potential sites exist, and they cause large electron scattering and hence resistivity. Second one is crystal defects. The presence of imperfections such as vacancies, grain boundaries, changes in periodic potentials. These are called crystal defects. Imperfections in the crystal, like vacancies and a void. Some atom should be there, but it is not there. That is called void or vacancy. And grain boundaries grain boundaries also will be there. So up to some extent, it will have some periodicity. After that, atomic arrangement will be in different fashion. So the grain boundaries changes the periodic potentials. So larger the number of defects, larger will be the non-periodic potentials, and hence larger the electron scattering and resistivity. Third one is thermal vibrations. Thermal vibrations. At high temperatures, the resistivity is linearly proportional to absolute temperature. At high temperatures, resistivity is linearly proportional to absolute temperature. I already shown you in the graph that if temperature is raised, resistivity is also increases because of thermal lattice vibrations. They are linearly proportional. If one is increased, resistance also increases. Whereas at low temperatures, the resistivity is proportional to fifth power of the temperature. This is at room temperature and higher temperatures. Okay, linearly proportional they are. But what about at low temperatures, below the room temperature and very much lower temperatures? What will happen to resistivity? What will happen to resistivity? At high temperatures, resistivity is linearly proportional with respect to what? With respect to one another, resistivity and temperature. At low temperatures, it is proportional to, at low temperatures, resistivity is proportional to fifth power of the temperature. Fifth power of the temperature. That means rho is proportional to T power 5. Due to thermal vibrations, the positive ions move away from their ideal positions, okay, due to thermal vibrations. If temperature is raised, because of thermal vibrations, the positive ions move away from their ideal positions, so that periodicity of the potential changes. With an increase of temperature, the amplitude of thermal vibrations of positive ions will be more, so non-periodicity increases. Amplitude of thermal vibrations of specific ions, positive ions, will be more. So non-periodicity increases, hence resistivity increases. Rho is proportional to T at high temperature. Rho is proportional to T power 5 at low temperatures. Okay, near absolute zero of temperature, the resistivity of some metals drops to 0. At low temperatures, resistivity will be lower because there are no thermal lattice vibrations. Then electron can move freely. Hence, they show superconductivity. For some materials, the resistance is not equal to 0 even at 0 Kelvin. So that the total resistivity of a metal is due to impurities and defects and also due to thermal vibrations. So rho is actually rho I plus rho T. Resistivity due to thermal vibrations, rho of T. Rho I is actually, it is the resistivity due to impurities and defects. So total resistivity of the material is rho I plus rho of T. Okay, so with this, we are done with this particular topic, origin of resistance also. Fermi-Dirac distribution will now go for, if possible, I will send the same link, otherwise I will send another link. Be online.